Okay, before I begin, I would just like to express my great gratitude to Doug Lee and to John Rose and John Tristan and Brian Getz for helping me to brainstorm some of the ideas that I'm going to be talking about this morning. And there are 2 or 3 different stories I'm going to tell you about projects I've been working on or things I've been thinking about. And I want to begin with actually a very old story in Modern Guys, and this is prompted by an essay that I read by William Cook about data abstraction. This is in the 2009 OOPSLA conference. And in his essay, he makes a very interesting distinction between abstract data types and object-oriented programming, which was something that had sort of been muddled together in my mind. He draws a very interesting distinction. He says that abstract data types encapsulate the implementation of a type, whereas true object-oriented programming encapsulates implementation of the instances of the type. And roughly speaking, this has to do with with exactly how the instances of the type play with each other. And after meditating on this essay for some time, I've concluded that while we think of Java as being an object-oriented language, actually in its structure it's more ADT-like. And doing true object-oriented programming in Java, which sometimes you want to do and sometimes you don't, so it's nice that Java gives you the choice. But if you want to be truly object-oriented, this requires a little bit of discipline in how to use language and perhaps needs some extra help. And one of the things I'm going to be talking about is what kind of extra help you might need. And let's get rid of this little notice here. There we go. So I'm going to show you an example. I like code. I'm going to show you lots of code. And this example, after the example in Cook's paper, is a simple data structure. We're going to represent a set of long values. So here's an interface long set, and it has several methods, one to test whether the set is empty, one for adding a new element to the set, one for unioning 2 sets, one for deciding whether a set contains a given value. And we've got this global value empty, which is just the empty set. So that's a sort of singleton kind of pattern. And as an example, we might start with long set empty and adjoin the value 1 and adjoin the value 2, and then union that with a different singleton set that contains 3, and so now we've got a set that ought to contain the values 1, 2, and 3. So if we ask it whether it contains 2, we expect the answer true. Okay, with me so far? Okay, this so far is quite elementary. So here's the implementation of EmptySet. And I'm going to have to ask you to forgive me my strange style on the closing braces. It's either that or make the font size for the code 20% smaller. This allows me to fit things on the slide. So here's a very straightforward implementation of EmptySet. It implements long set. The constructor is trivial. If you ask whether it's empty, it says true. If you want to adjoin something to it, we're going to return a new AdjoinSet object. We'll see the code for that in a minute. And there's a special case when you're taking the union of an empty set and something else, you can just return to something else. And finally, if you ask whether the empty set contains anything, it says false all the time. Okay, now let's look at the implementation of AdjoinSet. This is the classic thing you would expect if you were implementing a set as a list, you know, with cars and cutters, as in Lisp. We're going to have the AdjoinSet contains an item and also a pointer to some other set which contains the rest of it. And the constructor, again, is trivial. It just sets up these 2 fields, item and rest. If you ask whether it's empty, it returns false because it knows it's got at least one thing in it. And to adjoin something to this very adjoined set, we just make a new AdjoinSet object. That's straightforward. That's like consing the new element onto the front of a list in Lisp. For our unions, we're going to make a new union set consisting of this set and the other set we were handed, and we'll see the union set object specification in a moment. And finally, if you want to know whether this set contains the value x, well, it contains it if either x is the item in this very object, or if the rest of it contains x, one or the other. So we use an OR construct. Okay, now I'm going to refine this implementation 2 ways. One of the reasons, of course, is that we do this abstract implementation and have interfaces and so forth, so we can change the implementation and change the performance characteristics of the set implementation. So the first modification I'm going to make is to change the definition of adjoin. So instead of simply constructing an adjoin set, we first check to see whether this very set already contains x. If so, we don't need to adjoin it again. So we're just avoiding adding duplicates to the set. And this has nice space properties, but on the other hand, it has a time cost because it takes time to do that contains check. So if you make very big sets, you might find yourself spending a lot of time on containment checks. But on the other hand, it keeps the space used small. So that's an interesting trade-off. And finally, I want to show you that I'm going to change the definition of contains. I'm going to be a little more explicit about it. Instead of using the Boolean OR operator, I'm going to use an if-then-else statement. So we say if X is the item, then we return true, and otherwise we return the result of calling contains on the rest of it. Okay, here's the implementation of UnionSet. And it also has two fields, set1 and set2, and the constructor is trivial. And this set is empty if either if both set1 is empty and set2 is empty. Now, because of the way we set up unioning the union method for the empty set, if we take the union of the empty set and something else, we will just get to something else. We're not here optimizing the case of union set and unioning with the empty set. That's something we could have put into the definition of union here. The union method, I didn't bother. That's an optimization we could choose to put in. Instead, the implementations of adjoin and union are exactly as they were in implementations of some of the other objects that implement long set. This looks like a great opportunity to do some code sharing and provide default implementations in the interface. Fortunately, that's a coming feature. And finally, to decide whether one of these union set objects contains X, we simply ask set1 whether it contains X. If it doesn't, then we have to check with set2, and it's the OR of those two cases. Okay, again, all fairly elementary, the kind of thing we would expect a freshman college student to be able to code. This one is a little more interesting. Suppose that we want to be able to support some very large sets very compactly. So this class multiples of also implements long set. And again, this example is after Cook. And its constructor takes a single value X, which will get stored in the field factor. And the idea is that this set represents all multiples of that factor. So if I say multiples of 3, then all the multiples of 3, at least all those that are represented as longs, are elements. And if we'd chosen to use big integer instead of long for element representation, then it truly would represent an infinite set. So that's kind of cool. A multiples of set is always non-empty, so isEmpty returns false. The implementations of adjoin and union are exactly as before. And the contains test is interesting. If you ask whether a multiples of thing contains a value X, well, there are two cases. One is where the factor happened to be 0. Everything's a multiple of, I'm sorry, everything is not a multiple of 0. I got this test wrong. Ooh, I got a bug. But in any case, you need to check whether the factor is 0 and handle it appropriately. So if the factor is 0, you actually need to check to see whether X is also 0. And otherwise, you see whether X remainder of the factor equals 0. Okay, code walkthroughs are good. They reveal bugs. Okay, so I showed you all the code for implementing different kinds of sets. Now let's look at some of its properties. We can write an expression such as, let's make a new multiples of 2, union that with a new multiples of 3, then adjoin 7 and 43 just out of strangeness. And then we can expect this compound set object to behave as if it contained all long values that are a multiple of either 2 or 3, or both, as well as the values 7 and 43. And despite the fact that this set contains a very large number of values, conceptually it has a very compact representation. Now here's a simple use case for this wonderful set library we've built up. Here's a class set test, and it's got a public static void main. Everybody recite the public static void main string open close args. I typed that over and over again. Maybe I shouldn't. And we're going to start with this set S consisting of just the value 2 because we know that 2 is a prime number. And then we're going to start candidates at 3 and have this while loop that keeps incrementing the candidate by 2. Essentially what we're going to do is we're going to gather together the first million prime numbers. And we've got this counter int, and while the count is less than 1,000,000, we look at the candidate. If it's prime, we adjoin it to the set and increment the count. We keep doing this till the count reaches 1,000,000, constantly bumping the candidate by 2, so we're testing all the odd numbers to see whether they're prime. We've already included 2. So maybe I've already done some premature optimization here, counting by 2, which is a classic thing to do for this kind of thing. So we build up this set of 1,000,000 prime numbers, and then we ask whether the set contains 13, which is a known prime number. Does this print true or false or something else? Anybody? Anybody else? I tried it. That's what it prints. Yes, Stack Overflow error. That's exactly what's going on. And I told you this is an old story, and in fact, I expect most of you to know it. Thank you for not ruining my punchline. What's going on, of course, is that it's overflowed in the contains method of AdjoinSet, because we built up this long chain of adjoins objects, and down here at the bottom you can see that I've marked in red. The contains method has a recursive call to the contains method of the rest object. And since we built up this thing 1,000,000 long, we're trying to do 1,000,000 recursive calls, and my stack overflowed. Okay, yes, this is the story about why tail calls are good, or can be good. And this is again, an old story, and many of you in the room may already believe in this story, and so if you are still a skeptic, I hope to persuade you, and if you are not a skeptic, I'm hoping to provide you with some additional anecdotal fodder to present to skeptics. What can we do to fix AdjoinSet so we avoid the stack overflow error? Well, a classic thing to do is to get rid of the recursion and replace it with a loop. And so here is a recoding of that. We ask if we want to find out whether the AdjoinSet contains x. We make a variable z, initialize it to this, and we're going to iterate by constantly saying z get z.rest, as long as z is not empty. And if z, z is a pointer that runs down the chain, and when it runs into a z whose item is equal to x, then we found it and we can return true. And if we go down and find an empty set, then we return false. And this would work great if all we had were adjoin sets and empty sets. We've got other implementations of long set here. And in fact, there's a type error here, which is that we've declared the variable z to be an adjoin set, but in fact the type of the rest field, when I say z get z.rest, if you look up at the top of that slide, you see that the type of rest is not adjoin set, it's long set, which is a bigger type. So in fact, that update of z equals z.rest has a type error in it. And to fix that type error, you have to take all those other possible implementations of long set into account, including the ones we haven't implemented yet, including the ones that the guy in New Zealand or India is going to implement tomorrow that I haven't thought of. I just picked those as places that happen to be far from me. Okay, so we can try to fix that up by doing it this way instead. Instead of declaring the variable z to be an adjoin set, we'll make it a long set. And now we need to do the instance of checks and the adjoin set casts and so forth to make all this work. I also had to lift the declaration of z out of the for loop and put it up top, a classic sort of yucky idiom you have to do. So that down at the bottom, if I chase down the chain of adjoin sets and find something that isn't an adjoin set, then at that point, then I can call the contains method whatever that guy is. And so at that point, hand them off to the end. At that point, I do make a recursive call. So this solves the problem for chains of adjoin sets, but what if there are two sorts of set that form long chains? For example, I could have implemented multiples of in such a way that it wasn't self-contained, but actually had a rest pointer as well. So it would be sort of an adjoining multiples of thing. And then I'd have two different kinds of things that could form chains, not only within themselves, but with each other. And whenever I switch types, then I'll have this recursive call, either that, or I will have to have each of their contains implementations know about the other one, and I've blown away abstraction. Well, suppose I try to centralize the implementation of the central loop that avoids the recursion. Maybe I should use an iterator of some sort and use the iterator abstraction. But now I've got a problem here that I've got this multiples of type, and iterating through all of the values it represents could take a long time. In fact, if I were using big integers, it would never finish. And so, so that's a problem too. So iterators don't quite solve my problem in this case. So what's happened here is that in the effort to get rid of the recursion, I found myself having to break abstraction and reach into the implementations of other objects and know about them so that I can construct this type loop. And I spent some time trying to figure out how to explain what's going on here. For today, I think the way to explain it is that sometimes what you want is a finite state machine. Finite state machines are important models in computer science. It's not the only model. There are also Turing machines and stack machines. The JVM model is fundamentally a stack machine. But if that stack machine structure forces you to carry along a stack of return addresses even when you don't want to, then the state ain't finite anymore. And if you're trying to use the JVM to implement the finite state machine, you're being forced to carry along extra state that is conceptually not needed, namely the return addresses, for places you really don't care about returning to anymore. Now, sometimes that return state is very valuable for things like debugging, but that is an extra linguistic feature. It has more to do with the tool set rather than what you're actually trying to say in the language. And so in order to get around this problem, we use loops for the simple cases. And for the cases that aren't simple, we simulate finite state machines. For example, we use a simulated program counter by using an integer variable or something, and have a loop around a big case statement. And as each branch of the case updates the simulated program counter, and then you go back around at the top of the loop and you do a redispatch on the new program counter. This is a familiar sort of pattern that people program in these cases. The problem is there's no good way to break the finite state machine graph and modularize it without running into the return value getting pushed on the stack problem from the recursion. There's no good way to break up the finite state machine graph, and this matters when the method size is limited, as it is in the JVM for various good reasons. If you make a big enough simulation of a finite state machine, you'll find that your method size goes above 2 to the 16th, and you've got a different set of problems. And in fact, as John Rose pointed out to me, if the JVM only supported proper tail calls, we would have a way around this limit on method size. The compiler would have half a chance of actually automatically breaking up a method. I'll talk about that more in a minute. But without that, you can't modularize the finite state machine. It's a stylistic problem. So here's an analogy I thought of last night while sitting on an airplane and thinking about airplanes. Imagine an air traffic system where there weren't any one-way tickets, only round trips. And in fact, our current airplane system, most trips are round trips. It's kind of well optimized for round trips, but occasionally that's not what you want to do. So suppose you wanted to start at San Francisco, visit Boston and Dallas, Fort Worth, and then return to San Francisco. But all you've got is round trip tickets. Well, you could go round trip San Francisco to Boston and then round trip San Francisco to Dallas, but you've gone more distance than you'd like. Or you could get a round trip from San Francisco to Boston, and while you're in Boston, do the round trip to Dallas. That's okay too, you've still kind of gone out of your way. And if you're more than 3 cities are involved, then it gets increasingly ridiculous. In this case, what you really want is a triangle trip. From San Francisco, go to Boston, and remember that you want to get back to San Francisco. Now from Boston, go to Dallas, Fort Worth, and pass along the fact that San Francisco is your return point. You don't care about Boston anymore. And then finally return to San Francisco. This is a precise analogy for what you're doing with tail calls. It's not what you want to do all the time, but when you do want to do it, it's really important. So I come out of something of a background in somewhat functional languages, and in those languages it's been customary not to specifically mark tail calls. You're just supposed to know which calls are tail calls and which aren't. It's obvious from the syntax of the language. That's a little less so in a language like Java that has supported a variety of programming styles. And so I've come to believe that, in fact, it's a good idea, at least in these broader use languages, that tail calls should be marked, because there are actually 3 cases of interest to the programmer. I want to call that guy, and I want an answer back, because I need to come back here and do something else. And the other is, I want to go there, and I'm sure I never want to come back. And there's a third case where, well, happens to be a tail call, but I really don't care. You figure out the right way to implement it. If pushing a return address on the stack is actually faster, go for it. So the way I would like to code the contains method of AdjoinSet is say, if you're given x and x is equal to the item, then return true, and otherwise go to the rest object and never come back. Ask his contains method, he's got the answer. And conveniently, the goto keyword has been reserved in Java all these years. So we could just replace return with goto, and it's pretty clear what you mean. I'm not saying that's the only syntax possible, but it's very cute, and I'm not the only one to have observed that. So when we do this, I will claim that we are coding the AdjoinSet object, and in particular its contains method, in a pure object-oriented style. And what I mean by this is that each instance of the object is responsible for its own behavior, and it doesn't go mucking about in the representation of some other object, even if it happens to be its twin brother, in order to find out about its internal state. Whereas if I decide to use an explicit loop like this is more of an abstract data type style, where for objects that are not of my kind or not of my tribe, then I continue to be object-oriented. And when I fall through to if I chase down the chain of AdjoinSets and haven't found what I wanted, then I do the object-oriented thing and say, well, I don't know about you, you take care of it. But for guys who are like me, guys who are other AdjoinSets, I feel quite free to reach inside their representation and grab their fields, even though they're not my fields, but they are of my type. And that's what we mean by an abstract data type, as opposed to being purely object-oriented. And there are advantages to being able to do that. So to summarize, the advantages of proper tail calls, having proper tails in a JVM, would include providing good support for coding finite state machine models of all kinds, and for supporting modular representations of those finite state machine models, and more specific than that, being able to code them in a purely object-oriented style, taking advantage of object-oriented abstraction, not just ADT style abstraction. This in turn would give us the ability to automatically break up large methods, because if you think about it, each JVM method as it's currently structured is a finite state machine. It's got a finite set of argument and local variables sitting there, and it's got a program counter that wanders from place to place. And the bytecode can be analyzed into a control flow graph connecting basic blocks. And if you could only take that graph and then break up that graph and put it in separate methods, and then being able to call among them without increasing the stack, might not be the absolute most fastest way of doing it, but would be a possible way of taking big methods and breaking them up in a compiler. It's just a matter of modularizing the control flow graph and providing a way to transfer control among the different chunks of it without increasing stack state. And finally, perhaps most important, if the JVM supports proper tail calls, that helps not only Java, but also all the other languages that want to be targeted to JVM. I was recently asked to review a paper for a certain journal, and this is a paper on a functional language, and because that paper is still under review, I can't break confidentiality. But I will paraphrase one remark from that paper, and he said roughly, our functional language has all sorts of great features, and they're very different from Java, and it's all funky and wonderful. And this paper is about how we managed to compile these all to JVM, even though JVM wasn't designed for them. But the one remaining problem is tail calls. We can't seem to overcome that, and this is a real pain for us. So when it comes to situations like this, avoiding pushing a return address on the stack isn't just an optimization. The phrase tail call optimization has become prevalent in the literature, and that's a shame. Because the real truth is that subroutine call instructions in architectures dating back to the 1960s have actually encapsulated a tail call pessimization. That is requiring you to save a return address, even that's not a new return address, that is, even if that's not what you want to do. Instead, what we need tail calls because those support the ability to code finite state machines in a natural and modular and, in fact, purely object-oriented manner. So please, 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 I would love to see proper tail calls in JDK 9. Little late desperate in JDK 8. They have so many advantages. And I said this is an old story. This is something we've known for over 17 years. It was back in 1996 that Bill Joy and I went to the then Java team management and said, tail calls are going to be really important. Could we please put them in the next release? They said, well, we're busy fighting other fires. We'll put them into the next convenient release. And I guess that promise was kept. It hasn't been convenient for 17 years. Please, please, JDK 9. But in fact, we haven't known it for over 17 years. We've known it for over 34 years. It was in 1978 that I wrote a paper called Lambda the Ultimate Go-To, which is actually something of a misnomer. It's not the Lambda that's the go-to, it's calling it that's the go-to. And this is something that was in the scheme programming language from the beginning. And from that heritage, functional programming languages have tended to adopt the tail call as a style of programming. But there are reasons to do it in Java as well. And it was hard to do 10 years ago, but we've reached a point where it's a lot less hard to do because we now much better understand the JVM implementation issues. We understand some of the JVM security issues. I understand that the JVM security code has been restructured a little bit. That should make this a lot easier to do if we should sit down and choose to do it. Okay, so now for something completely different. I knew you wouldn't want to hear me just rant and whine this morning forever about tail calls, although I think it's a very important topic. Tail calls are something that are very important to the sequential style of programming. Finite state machines tend to be this sort of sequential model. You chunk along doing one thing at a time. But sequential programming isn't everything that's going on anymore. Now I'd like to talk a little bit about parallelism and some things I've been doing in the parallel arena. Some of you may know that I worked on a research language called Fortress for close to a decade, trying to understand some of the issues of implementing parallelism. And what I'm going to talk about this morning is a little bit of the fruit of that. Although that project is wound down, there are some lessons that we learned. And in fact, it had some influence on Java over the years. So a cool thing that we're getting in JDK 8 are these streams and splitterators and the whole Lambda project thing. With this, Java is becoming somewhat more functional in style. And the interesting thing is that so are a lot of other languages over the last decade. And what I'm seeing, looking at Java and Scala and Ruby and Haskell and a bunch of other things, there seems to be sort of convergence happening, a sort of forming consensus on how to represent and process collections in such a way that they're amenable to parallelism. And this is it's not surprising that part of this consensus is that avoiding side effects helps you out, because side effects make synchronization very difficult. What is surprising, I think, is that the convergence in fact involves the use of higher order functions and lambdas. We are using things like map and reduce. Maybe it's just the popularity of MapReduce and Hadoop and things like that. But I think there's something more fundamental underlying it that I haven't yet figured out how to articulate the way I have about tail calls, which has taken a long time. But there's something about the use of higher order functions and lambdas that seems to make this easier to organize. So instead of giving you an explanation, I'm going to give you a slogan. I've been known for saying in the past that Java dragged a lot of C programmers about halfway to Lisp. And what I meant by this was that there was this killer feature, garbage collection. And this had some consequences. In order to support the garbage collection, you had to do things like check the null pointer dereferences. You had to bounds check the arrays. And you had to have a good type system, things like that. But the killer feature was the garbage collection, which freed the programmer from the burden of allocating memory. And I think we're on the verge of the next revolution, which is that maybe next Java will drag these same programmers, or the current collection of programmers, about halfway to Haskell. And the killer feature here is automatic parallelism. Just as garbage collection manages automatically the allocation of memory, automatic parallelism can manage the resource of processors. And that's all there is, memory and processors, right? Once we solve this problem, we're all done. Well, maybe not. Nevertheless, I say hooray for JDK8 for making some good strides in this direction. Now, here's a somewhat related project that I've been working on for the last year, the problem of generating pseudo-random numbers. And it's not obvious that this would fit in the framework because random numbers are a kind of side effect. You call a method twice and you get 2 different answers back. In fact, you expect to get 2 answers back. I missed the opportunity also to put up the Dilbert cartoon where Dilbert is visiting the accounting dungeon, and there's an accounting troll down there that's just sitting there saying 99999, and it's explained to him that this is their random number generator. And Dilbert asks, "Are you sure it's random?" And the troll replies, "That's the problem with randomness, it's so hard to tell." We're expecting you to get different values. But it's a side effect of a limited form. When you think about it, pseudo-random number generation is actually another form of resource allocation. It's a little bit like new. You want to get new ones, and it's just that sometimes you accidentally get the same value twice. But when? Well, that's interesting. Characterizing that mathematically is a very interesting problem. So consider a class like java.util.random, but besides having a method like nextLong, which gives you the next random long value, whatever that means, it's also got a split method. And the job of split is to make a random number generator look sort of collection-like. Well, think of a random number generator not as generating a sequential stream, but as providing a collection of numbers that have interesting statistical relationships when considered as a set. And one of the things we're going to be able to do is to take this collection and split it in 2 pieces so that each one can then in turn be used as a source from which to draw random numbers. And we'd like to be able to do this splitting recursively. So it's sort of collection-like, and with this interface you can make a splitterator for it, and you can get a stream from it. So you can say, hey, random number generator, give me a stream of longs. And now I can use this in string expressions and process it with map and reduce and all that stuff just the way I would anything else. And this turns out actually to be surprisingly effective. Now, what do you need to do in order to guarantee good behavior? You certainly don't want the result of calling split on a random number generator to generate the exact same values as the random number generator itself. So just cloning it isn't the answer. In fact, characterizing exactly what you want to do is kind of subtle. You could say, well, if we split the random number generator, then the result is 2 objects, the old one and the new one. And together they generate exactly the same values as the original one would have. It's just that some come out of one and some come out of the other. Turns out that requiring that precise a partition is overkill and actually makes it very hard to implement the split operation. So we settle for something a little more subtle, which is that the 2 random number generators are linked mathematically in such a way that if you use each of them to generate some numbers, then the collection has the same good statistical properties as if you had used only one of them to generate that. And it's also subtle making that happen. My work has relied on a paper that appeared at last year's PPOP conference. This is by Leisers and Chartle and Suka. I've also been studying other papers. Other researchers have been studying the same problem. There's a nice paper at the 2011 Supercomputing Conference from D.E. Shaw Associates. And there are others as well. But roughly speaking, what you want to do is to make random number generators be data structures that share a mathematical property but don't actually share any data structure. And we've managed to achieve this. So we have implemented a class splittable random that compares favorably to java.util.random. It has a somewhat longer period. I wrote much longer period on the slide, but its period is 2 to the 64th instead of 2 to the 48th. And the technique can be used to make even longer period random number generators. It passes good statistical test suites that java.util.random fails, including the die-harder test suite. It has the interesting property that, as I said, if you make many random number generator objects by splitting, they don't share any mutable state. And as a result, it's very easy to process them in parallel. And here are 2 sample benchmark results. I made a very trivial sequential Monte Carlo benchmark, just calculating pi by throwing darts at a square and see how many of them fall under the edge of the quarter circle, and the ratio tells you what pi over 4 is. And we ran this benchmark using random and splittable random, and the splittable random version was 4.5 times as fast. Now, the amount of arithmetic they're doing is actually quite comparable. I think what's going on is that java.util.random is thread safe. So every call is synchronized. There's some synchronization going on there. I think that synchronization overhead is what's killing it. Splittable random objects, curiously, while they are designed for parallelism and therefore are not thread safe. They're not designed to be shared among threads, they're designed to be split across threads. And that's an important lesson to learn going forward, is that if we're going to use parallelism effectively, we actually don't want to be thread safe. Instead, we want to divide up the work in such a way that the different objects are not stepping on each other and therefore don't have to be thread safe. So when used as directed, this works great and gives us a 4.5x speed up. The next thing that Doug Lee tried, I haven't actually seen his precise source code, so I can't answer detailed questions about it. But he, roughly speaking, just took one of these splittable randoms and said, please give me a stream of longs, and then call the sum method on that for some suitably long stream. And he implemented, used splittable random and also implemented a splitterator sort of thing using java.util.random, and found that the splittable random version was 2,900 times as fast. Okay, this does not tell us that splittable random is wonderful. It tells us that something happened in the java.util.random version, that when you coded it up in the obvious way, it fell off a cliff. And again, I think it has to do with some sort of sharing problem, some sort of synchronization problem that hadn't been figured out. And that could be optimized and engineered. But on the other hand, isn't it great that splittable random actually did a decent job just right out of the box? This is on a 32 processor machine. So it's heartening that just organizing things the right way gets you good parallel performance right out of the box. And so I think this is confirmation maybe that we've developed a good framework, the splitterator and stream framework for describing this kind of parallelism. Because when we generalized it to an application that we hadn't originally envisioned, doing random numbers rather than collections, it all still kind of worked and everything interoperated pretty nicely. Furthermore, using that splitterator framework helped us to organize the pseudo-random number generation code better. And that helped us to see how we could better tune it for speeds. In fact, Doug Lee and I have been in a tight loop for the last month. It's been great bouncing code patches off each other and getting continual improvements to this random number framework. So we have some hopes that this will prove to be a useful object in the future. Okay, I'm going to finish up, and I'm going to finish up a little bit early. We'll have more hallway time. But I want to go into a war story about some of the low-level details of what we encountered doing this random number generator stuff. And it's not just because I love low-level code and I love war stories, but because it makes a third point, which I'll use to wrap up the talk. So down in the center of this algorithm, roughly speaking, there's a seed value. If you've ever looked inside the code of a random number generator, you very often find a variable called seed. It's the state that's being held. And there's this other value called gamma, and it's called gamma because that was the term that was used in the Lyserson paper. And roughly speaking, what we need to do is we need to take the seed, add gamma to it, and store it back. But the wrinkle is that we're not doing the arithmetic mod 2 to the 64th, we're doing it mod some weird prime number. So if it doesn't overflow, then everything is great. And if it does overflow, then there's some nasty fix-up code, which I've just indicated here by method call. So we save the seed value aside in a long variable, we add gamma to that, store it back into seed, and then we ask, is seed less than s? This is actually an idiom to find out whether overflow occurred. It's too bad we don't have access to the overflow flags. It would be wonderful if the compiler would recognize this idiom and actually use the overflow flag. That would be great. But even if not, this is still pretty reasonable. Okay, so far so good. Now, the war story has to do with experimenting with a 128-bit version of this. And Java doesn't have 128-bit integers. Fortress did. Fortress is dead. Too bad. Wish Java had 128-bit integers, not big integers because I want to be fast. Okay, so here's what we're doing. And this should look moderately familiar to some of you. We're going to represent the seed as two longs. We're going to represent the gamma as two longs, thereby getting two 128-bit values. And we have to do the 128-bit add ourselves. So we're going to not only put, we're not only going to save the low half of the seed into S, we're also going to save the high half of the seed into H, and the high half of gamma into GH. We add together the low half of the seed and the low half of the gamma, store that back in the low half of the seed, and we need to find out whether that overflowed. If it did, then we increment GH to represent the carry. Then we add GH into the original seed high, store that back, and then check to see whether that overflowed, and if so, we need to do the seed fix up. Okay, so far so good. Actually. Pardon? I'm not sure gamma low is positive, and we'll get to that in a minute. Actually, what's going on here is that we are, because we don't particularly care about the exact value of seed, we just want to keep incrementing it. We're using a strange representation for seed where each of its components actually is offset by 2 to the 63rd. And this allows us to use signed comparisons instead of unsigned comparisons, which we could use in JDK8 because we've got methods in the long class to let us do that. But I'm not yet confident that the compiler is going to do as great a job of recognizing idioms involving unsigned comparisons as signed comparisons, and also this allows me to test the code under JDK7. So all the usual engineering yada, 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 but thank you very much for the question. Yes, ideally this would all be done with unsigned arithmetic, and that would be evident in the code, but because of the particular application, it turns out not to matter, and I'm getting away with murder here. In fact, there's another problem with what's going on here, which is that my check for overflow isn't quite correct because the incrementation of GH might overflow, and I'm not testing for that. Yep. Okay. So we could make the test even more complicated, but instead I'm going to fix it another way, specific to a particular application. And this introduces an idea that really hadn't occurred to me before, which is there are ways of making code faster without changing the code. Instead, you tweak the data. So it turns out we've got some wiggle room in our choice of gammas here for this particular application. There's a trade-off between the number of significant bits in the gamma constant, that is the number of bits that are allowed to be 0 and 1, and the mathematical quality of the random numbers. And working at the 64-bit level, we really can't afford to give up any bits for that purpose. We're just about at the hairy edge of what's reasonable. In fact, the 32-bit version of the algorithm doesn't work at all because that's just too few bits to get the mathematical statistics you want. But up 128 bits, we can afford to give away a few. So I'll give away 12 bits at the top of gamma, and therefore make sure that the high order word of gamma is positive. And therefore, when I increment it in the third line of that code, that's guaranteed not to overflow, and that fixes my overflow bug. This has the additional benefit that because the gamma value is small, in fact, overall overflow out of the high word occurs fairly rarely. Therefore, I call the seed fix-up routine fairly rarely, and so it gets amortized over a bunch of iterations of this little inner loop. Is that okay? Can I get away with that? You know, doesn't making the high order 12 bits of gamma bias the weird mathematical statistics in some way? Well, frankly, I'm not enough of a mathematician to be sure about that, and that's something I want to research further in the future. However, doing this seems to leave the actual statistical tests that we run, the die-harder tests, are completely happy with this. And there are some theoretical reasons to think that this is okay. But so this is nice because the seed fix-up routine is a fairly expensive routine. Now we're calling it only about one time in 4,000 or maybe one time in 2,000. The statistics are a little strange. And so the cost of the seed fix-up routine has nearly disappeared, which is great. But there's yet one more thing we can get out of it, which is, let's also make the high 4 bits of the low word 0. And I've shown that down here at the bottom with that red 0 here. Can we get away with that? Are the statistics okay? Well, the die-harder tests seem to like it. That's all I got to tell you today. We're looking into running a bunch of other more stringent statistical tests. We're looking into trying to figure out the mathematical theory behind this, but so far it seems to be okay. And the benefit of this is that it makes that incrementation of GH in the third line fairly rare, because most of the time you are not overflowing out of the low half either. And this improved the speed, this one tweak, so assume that I'd already done what was on the previous slide, so we're not calling seed fix-up very often. But this last tweak on this slide gave another 12% improvement to the overall Monte Carlo benchmark. And that startled me because avoiding that incrementation is much less than 12% of the overall cost of one loop of the benchmark. As nearly as I can figure out, what we're saving is that branch instruction, seed low less than X, has now become highly predictable. And what we're avoiding is the unpredictable branch, but I need further investigation on that too. But again, it's startling that such a very simple change to the data could have such a large effect on the runtime behavior of the program without actually changing the code. Now, what I'd really like is the compiler to recognize that third line is an idiom for add carry. And what I'd really like is an add carry instruction, just not have to worry about having a branch instruction there to begin with. Then I wouldn't need this trick with the data. But the trick with the data works on compilers that do and compilers that don't, and it seems to be a good thing and with no downside, so why not? Well, the downside is I've got to document and explain it in rooms like this, and do you really want 5 minutes of your life back? I don't know. But I thought it was cute. So to conclude, it looks like parallelism is going to be a big, important part of the picture in programming globally, not just Java, not just the JVM, but parallelism is important. We see that coming. I've seen it coming for 30 years, so have a lot of other people. But it's here, it's now. We've got a good story for JDK8, and we hope we can support other languages as well, not just Java, in exploiting this kind of parallelism with a minimum of fuss on the part of the application programmer who has other things to worry about. On the other hand, sequential programming also continues to be important, and we hope we can support other languages as well. And if at last we implement proper tail calls, that will be one more step towards supporting good sequential styles of programming for particular kinds of applications. So parallelism, big picture, sequential programming, big picture, but also low-level detail can sometimes really matter. You don't want to worry about it too often, but when it does and you can get that extra 12%, that's really satisfying. We need good tools, good JVM support for all three, and I'm hoping to hear a lot more about all three of these topics during the remainder of this conference. Thank you.